Hi, my name is Victoria Hyatt. I am currently a senior in high school and I currently reside in California. I started Polygence just a few months ago, and when I first came into it, I had a general idea of really what I wanted. I wanted to do something in engineering because I've had a lifelong passion for STEM, but I really wasn't quite sure what specific field I wanted to go into. And after talking with my mentor, Soha, for so long about different nuclear ideas, as she herself is a nuclear engineer, I finally decided to focus on molten salt reactors, as personally for me, that was one of the most interesting parts of the nuclear world. And so for my presentation, I will be talking about Neutronics evaluations of different carrier salts for MSRs. So the really guiding research question was, how do MSR fuel salts affect criticality? I modeled my simulations with four different carrier salts. Each of these were talked heavily in early research in the 1940s, 50s, and early 60s. And when I started with base geometry for all of them, just focusing on modeling the different reactors and the makeup of the fuel and the salt carriers. And then I started to change the geometry and compare the neutronics in the different geometry. So, to give a little bit of background on MSRs, the first successful MSR was in 1954 with the aircraft reaction experiment. I will later be talking about as the ARE. And this was followed in 1965 by the molten salt reaction experiment, the MSRE, which very, very creative name, I know. These were both at the Oak Ridge National Laboratory, and it's important that to note that these were both funded by the US government. But in 1970s and late 70s, the nuclear field started to become more controversial. And because of this, the US government slowly started to decline the funding in the nuclear field. Then in the late 1990s and early 2000s, there was renewed interest in MSRs with the Generation 4. There are many different countries that have picked up their research, notably mostly China, followed by India, the United Nations, Canada, and the US. It's a little disappointing to know that because of this gap in research, a lot of the research before the US started defunding all of this was a lot of it was classified. And because of the gap in research, a lot of it was not then, after it was declassified, brought to the digital age, which means we have lost a lot of work or it's buried somewhere, meaning that we have started to essentially recreate the research we had done so long ago. To give background on how I did my simulations, I used the OpenMC. This is an open source reactor simulation which allows you to build reactors and simulate them, which is done using Monte Carlo methods of calculating everything. This uses a sense of randomizing the how the neutronics work and how the neutrons react and affect the reaction. This is important as it more closely models how the neutrons would actually react in a real world environment. This was created and written first in 2011, and then it was published to the public to be used by universities and individuals and so many more in 2012. So there are four different nuclear salt carriers I model, and the first one was actually used in the ARE. And this was chosen because of its high performance in circulation tests. And then the second one I modeled, the BEF2, is actually talked a lot about in early research as being meant to pair with other moderators. It was mostly noted for its modification properties, but I decided to model it on its own because I thought it would be an interesting benchmark to see actually how the modifications properties work and how well do they work. And so I thought that was an interesting field to go into. Most notably, the BEF2 was thought to be used with NAF and lithium. So pardon me. So the third carrier I use is actually known to be the low-cost coolant, which is important if you want an economically viable reactor. It's important to save costs where you can. So for number 4, it is actually known as FLIBE in real world, and it is a very researched and popular fuel salt carrier for MSRs nowadays because of the ion lithium-7, which has a very low neutron absorption, which allows for a very continuous rate of neutrons affecting the fuel rather than being absorbed by the salt carrier itself. So for each of these different 4 models, I use a uranium fuel with U-238 and U-235 with an enrichment of about 4% for each of these. For the geometry of the pin cells, on the left, I have it depicted from the XY direction, and with the blue circle in the middle, that depicts the fuel rod, and the purple on the outside actually depicts the moderator. For the moderator, I chose a graphite moderator, which I simulated for all 4 of my different salt fuel carriers. And then on the right side, I have the XZ, and both of these were plotted using OpenMC Plotter. And then for the setting background, I used 1000 neutrons / particles. And for the point source, I have it at 0, 0, which is depicted in my picture to the right as the yellow dot. And this is modeled as an isotropic point source, which means that the neutrons aren't all spawned in exactly the same way at exactly the same speed. They're actually going in completely random directions with random speeds to more closely simulate how neutrons would react in the real world and in a real physical reactor. So I used 50 different batches to simulate the total K effective, which I will be showing in a little bit. So for the starting geometry, I started with a pitch of about 1.26 and a radius of 0.36. The pitch defines the bounding boxes, which defines the size of my moderator, and the radius actually defines the size of my fuel rod. So the scaling of my graph may seem a little misleading, as all of the fuel salt carriers for the K effectives are relatively similar, but also a little bit different. So for the next modeling of the geometry, I have a pitch of 126 and a radius of 36. Both of these have been multiplied by a factor of 100. It's interesting to look at how the K effective has drastically gone up for all 4 of the fuel salt carriers. And to explain a little bit more on what a K effective is, it is the ratio of the neutrons coming out of the reaction and the neutrons going in. So ideally, you want a K effective of 1. That means for every neutron put into the reaction, you're getting just 1 neutron out. But anything less than 1 is subcritical, meaning the reaction is in fact dying, which is not great if you want an economically viable reactor. And then anything much bigger than 1 is critical, and if it's much, much larger than 1, you have built a bomb. So looking at FLIBE and NAF/BEF2, both seem relatively similar to 1, but FLIBE is almost 5,000 parts per million away from 1, which means it is very critical. This is because in a reactor, this pin cell is just modeling one part of a core, which would have many, 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 many different pin cells. So it would be many of this exact simulation over and over and over again. So while it might not seem that far away from 1, in terms of the whole core, this would be very drastic. So this means that the optimal sizing for the pin cell for LIF and LIF-BEF2 FLIBE would ideally be between 1.26 and 126 for the pitch. So then I multiplied the pitch and radius again by a factor of 10. This is very interesting as the K effectives here have drastically increased or decreased, meaning that maybe against what is originally thought, the just increasing the size does not actually increase the K effective. This is because the moderator actually slows down the neutrons and absorbs them, meaning making the reaction die. So for my future, I'm really hoping to continue some sort on this field in 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 recent times. I've really become interested in this field, and I hope to continue in college. I hope to continue this in engineering, and whether I'm just taking my new research skills or the knowledge in the nuclear field in general, I've really become passionate about this, and I'm really excited about this and the research I've done, and I really hope to continue it in some way in the future. Thank you so much for listening.